All right, so now we're looking at section 4-4. We're talking about transformations of logarithmic functions in this section. And the first chart we come to is kind of a guide to show you how changing the equation in different ways will affect the graph of the logarithmic function. And it's really typically the same things that we've looked at before, because many different functions are translated in the same way. So all of these different movements we've already seen. Just to go back over it, of course, if you add something, you're going to be translating that many units up. Subtracting something, you'll be moving that many units down. Now, this one's a little bit tricky because of the way it's written here, and it's expressed as x minus d, and it says translate d units to the right if d is greater than 0. Well, if d is greater than 0, you might be thinking, well, coach, isn't that opposite of what it should be? If the d is plus, then isn't it to the left? Well, yes, but take a look at the form and the way that they have shown it here. So if d is greater than 0, that would be like plugging in 2 for d. Well, if you plug in 2 for d, what do you have? d minus 2. So minus 2 directly to x is going to move it to the right. And it works out. Same thing here. Like if d is less than 0, what if I plugged in negative 2? Well, it's minus negative 2. Negative and negative makes a positive, so it's really plus 2. Plus 2 moves it to the left. Okay, so it's just kind of an alternate way of describing it when it writes it in as this x minus d, right? But our rules are still the same. If it's plus some number, you go to the left that many. If it's minus some number, then you go to the right that many units. All right? Once again, if you're multiplying by a factor to the entire function, okay, it's stretched vertically by a factor of the absolute value of a, because remember, if it's negative, that's going to cause it to flip in the x-axis, right? So it's just the factor is the absolute value of a. So stretch vertically by that factor. If it's greater than 1, and then it's going to compress vertically, okay, by a factor of absolute value of a if it's less than 1. So if this number is bigger than 1, okay, stretch vertically, less than 1, compress vertically as usual. And then, of course, if the a is negative, it's going to reflect in the x-axis, okay? And likewise, if you're multiplying by some factor directly to the x, it's going to compress horizontally by a factor of 1 over k as long as it's greater than 1. And it's going to stretch horizontally by a factor of 1 over k if that number there is less than 1. So keep in mind that the factor is flipped. You must take the reciprocal of the factor. Then you're reflecting in the y-axis if the k is less than 0. Okay, reflect through the y-axis. And we've seen some of that as well. Okay. All right, so as we can see, a lot of the same movements and transformations that we've had in the other functions also will apply here to logarithmic functions. Now, the next thing that we take a look at here is we get into the idea of the natural logarithm. And so really, the natural logarithm, all it is a logarithm with base e, right? And remember, we discussed e when we were talking about the exponential functions and how it was obtained. And so if it's got base e, then that's referred to as natural log, and the denotation is ln. And so the natural logarithmic function y equals ln of x, it's the inverse of the exponential function y equals e to the x. All right? So if your base is e, you're raising that up to the x power. Then the inverse of that is not just a regular logarithmic function, it's the natural logarithmic function indicating that the base is e. All right, and so again, we have it defined here again. Y equals the natural log of x if and only if e to the y equals x for all x greater than 0. All right, and so once again, it's rearranged as it normally would be. Remember, when you take e to the y power equals to x and rearrange it, remember the natural log base e, okay, of x equals to y. The y is the exponent. All right, so it's rearranged in the same fashion as the natural log function. We've got them both graphs right here. We have e to the x that's graphed here, and we have the natural log of x, which is graphed here. And notice again, they're reflections of each other through the line y equals x. So graphically speaking, that would represent the inverse. All right, showing it graphically here. Then, of course, all the properties for logarithms, it also holds true for natural logarithms, because a natural log is just a type of logarithmic function. So it would still apply all of the properties. Okay? And we'll look into many of those properties here in the upcoming sections. All right? Okay, types of problems we're going to be looking at. Let's go ahead and look at a few of these now. So I want to use the graph of f of x to describe the transformation that results in the graph of g of x. So starting with f of x, changing the equation to g of x, what's the transformation that has occurred? All right, so that's what we're going to be looking at here next. And so again, we'll go ahead and we will graph that first function in here. So it's going to be log. Go to functions, miscellaneous, log with the base is what we want here. And so log base 3 of x. Okay. And so we have our graph here. Now, we want to know what happens if we change that to x minus 1. And so I've got another log function I'm going to plug in here. So again, it'll be log base 3. This time it's going to be of x minus 1. All right, so we've got them both graphed on the same screen here, and we can see what happened. Of course, whenever you subtract 1 directly to the x, that's going to move it one space to the right. All right, so no surprise there. We know that's what typically happens. All right, let's go to the next one now. So I'm going to clear this one off, and I'm going to see if I can't change this one to just log of x. All right, so there's log of x. Now, remember what we had said earlier? If there's no base indicated in the log, then it's understood to be base 10. It's understood to be base 10. All right, and if I wanted to illustrate that, if I pick the log with the base, if I put a base 10 down there, and then put an x here, look at what happens. It's the exact same graph because these are equivalent. That's the reason. So once again, if there is no base indicated in your logarithmic function, then it's understood to be base 10. All right, so no base listed means automatically base 10. All right, so we've got log base 10 of x. Now, what we want to change that to is going to be log of 2x. Log of 2x. All right, so let's see if we can determine now what happened here. Okay, so a log of 2x, and so it went from here to this lighter blue line. All right, so it appears that if I'm just looking at the graph and I see this happen, then I can say, well, it's either a vertical compression to make it smaller, a little bit smaller than it was earlier, or it could be a horizontal stretch to make it move like this. So let's see which one it could be. Well, remember, when you're multiplying directly to the number here, when you're multiplying directly to the number, right? Okay, so if that number is greater than 1, then it's going to be a horizontal compression, right? If it's less than 1, it's going to be a horizontal stretch. And so since 2 that we're using here is greater than 1, I know I've got myself a horizontal, let me see, where am I at here? Okay, I got a horizontal compression, right? Okay, so I've got myself a horizontal compression, right, by a factor of 1 over x. Okay, so really what's happening here is we've got horizontal compression, all right, and that's by a factor of 1/2, all right, horizontal compression, right, by a factor of 1/2, right, compressed by 1/2, okay. All right, let's try the next one. So in the next one, I'll clear it off, and we'll input the new graph, which is going to be negative 2. Go to my function, log base 10 of x plus 5. All right, so we can see what the graph looks like here, and that's the second one that I put in. Let me go ahead and put the first one in, which is log base 10 of x. All right, so now we're going to try to describe what happened here. All right, so first of all, multiplying by this factor, okay, the log by this factor, is going to start off by giving me a vertical stretch. Remember, so when it's here, okay, it's a horizontal stretch or compression. But when I go here, it's going to be a vertical stretch or compression. Since this is greater than 1, okay, it's going to be a vertical stretch by a factor of 2. Vertical stretch by a factor of 2, so no reciprocal like you have to do with horizontal. If you want us to verify, okay, we go here and take a look. So vertical stretch when it's greater than 1. So again, make sure you utilize that chart if you don't quite remember the way that the graph is manipulated. But that's only one movement. We have several here. The next one, we're adding directly to our x right here. And so that's going to also push it 5 up. All right, we know that. Okay. And the last thing that's happening is it's being reflected through the x-axis. Reflect x-axis. All right, so 3 different movements. Okay, it's being stretched vertically by a factor of 2. It's being pressed up by 5, and then it's being flipped across the x-axis. All right. And so those are the movements that we're going to be looking at here and describing on this one. All right. Let me see here. One more that we want to take a look at. And I actually graphed this incorrectly because I have misplaced my parentheses. So let me correct that. So that's going to go here, and that's going to be a +5. And so now we have the correct movement. And the up 5 part is the part that was missing there, right? And so, let's see. So now we got the vertical stretch in there correctly. Okay, the up 5, and then it's flipped through the x-axis. All right? Okay, so now we've got everything in there done correctly now. Okay, because I had input the 5 in the wrong place. I needed to correct that before I moved on. All right, so one more we want to take a look at. Let's see. And so for the last one, we've got natural log. All right, and it's going to be natural log of x. All right, so there's my original function, and so the new one is going to be natural log of negative x, and then +5. All right, and so when we are looking at these, right, the first thing that I need to make sure that I'm taking a look at here is we've got a movement, of course, and that movement, first of all, the +5 here directly to it. Okay. Now, remember, typically we're going to say that that's going to reflect it or move it by 5 to the left. However, remember, we've run into this situation before where if this x is directly negative here, okay, then remember how that's going to affect it. Okay, if I'm being pushed 5 to the left, well, once a flip occurs, that's actually going to make it move 5 to the right. Okay, so keep that in mind. This one is kind of tricky. 5 to the right is the actual movement, and of course, because of that negative, we're now reflected with the x-axis or y-axis. Reflect through the y-axis. All right, so both of those movements now are taking place, okay? Which, of course, now is verified by the graph, right? Okay, so flips through the y-axis and then pushes 5 to the right, okay? Let's see. And also, by the way, remember what we said? If you want to think about this as the natural log and think about it in this way, maybe. Have this rewritten as negative x minus 5, then you can kind of see where that movement to the right comes from when it's disguised like that and you rewrite it, you're able to see it. All right? Okay, so that's it. That takes us through both of the lessons for today, and your quizzes are waiting for you in Canvas, and I'll see you next time.